picture this for a second, if you will. You're sitting 5,000 meters above sea level.
Oh, wow.
Yeah, the air is incredibly thin, the wind is just biting cold, and all around you are these towering, jagged peaks of the Trans-Himalayan mountains in Ladakh, India.
That sounds intense.
Right. And you wrap your hands around a warm glass of fresh, local cow's milk just to ward off the chill. And it feels like the ultimate picture of health. A pristine, completely untouched paradise, just miles and miles away from the smog and the factories of the modern world. But, well, the reality of our modern ecosystem is actually far more complicated than that.
It is. I mean, it's a very natural assumption to make, right? We kind of instinctively equate geographic remoteness with environmental purity. We think, if we are far enough away from a highway or a smokestack, the food chain just has to be pristine.
Exactly, yeah.
But the borders between a bustling modern city and a remote mountain peak they're incredibly porous. Physical distance just doesn't protect the ecosystem the way we think it does.
Well, welcome to the Deep Dive. Today, we are unpacking a single, really fascinating piece of scientific research. It's titled Health Risk Assessment of Heavy Metals Through Cow Milk Consumption in Trans-Himalayan High-Altitude Region.
Quite a mouthful, but a really important study.
Definitely. And our mission today is to explore how extreme geology, rapid human modernization, and the fundamental mechanics of our own biology are all just colliding in one of the most remote places on Earth. And we're going to look at this massive global shift using just one everyday beverage as our lens, which is cow's milk.
It's the perfect lens, really, because to understand why this specific study matters so much, you first have to understand the sheer hostility of the environment we're talking about. I mean, Ladakh isn't just a mountain range.
Right.
Geographically, it is categorized as a high-altitude cold desert. So organisms living between 3,000 and 5,000 meters above sea level there are dealing with just an onslaught of intense environmental stressors, all simultaneously.
Okay, let's unpack this for a second, because farming is hard everywhere, So what makes this cold desert ecosystem so fragile when it comes to food safety? I mean, you're dealing with hypobaric hypoxia, right? Which means severely low oxygen levels combined with very low atmospheric pressure.
Precisely. And add to that freezing temperatures, minimal rainfall, and intense ultraviolet radiation, because the atmosphere is just so thin up there. It's an incredibly punishing environment for any biological system to handle.
Yeah, I can imagine.
And that environmental hostility directly dictates how the people there survive, particularly when it comes to food security. Large-scale, diverse agriculture is practically impossible. You can't just plant a massive field of wheat or vegetables and expect a high yield.
Which means the local communities have to lean heavily on livestock, cows, sheep, goats. They basically become the absolute anchor of human survival because they act as biological engines.
Exactly.
They can wander the mountains, eat this sparse, tough scrub and forage that humans could never digest, and turn it into highly dense consumable calories.
And at the absolute center of that survival strategy is dairy production. In an environment where, fresh produce is a total luxury, milk operates as this biological safety net.
Yeah, nutritionists often refer to dairy milk as a nearly complete food, right?
For a very good reason.
It's packed with proteins, essential fats, calcium, vitamins, and critical micronutrients. Nature designed it specifically to sustain rapid growth, making it incredibly efficient at delivering complex nutrition.
And here is the really dark side of this nutritional powerhouse. Because milk is so efficient at transferring nutrients, it is also a highly efficient pathway for transferring environmental contaminants right into the human body.
Yeah, reading through the research, that paradox really struck me. Milk is essentially a vacuum designed to pull nutrients from the cow's body and deliver them to the drinker, but it doesn't just stop at the good stuff.
No, it doesn't. That is the core paradox here. The biological mechanisms inside the cow that pull calcium and iron from the bloodstream to fortify the milk are easily tricked.
Tricked how?
Well, heavy metals are notorious for biological mimicry. Lead, for example, has a very similar atomic radius and charge to calcium. So when the cow's body is eagerly pulling calcium to produce milk, lead can essentially pick the biochemical lock, slip through those exact same cellular channels, and end up in the milk.
Wow.
Yeah, the cow's body thinks it's providing vital minerals, but it's actually passing along a neurotoxin.
So the very mechanism that makes milk life-saving in a harsh environment also turns it into this Trojan horse for heavy metals.
Mm-hmm.
But to get into the milk, those metals have to come from somewhere, right? It's like this invisible chain linking the geology of the mountains directly to human biology.
The pathway is highly systemic, yeah.
Huh?
It begins in the environment itself, the agricultural soil, the groundwater, and the surface water fed by melting glaciers.
Right.
If those compartments contain heavy metals, whether they're naturally occurring or from pollution, those metals get absorbed by the root systems of local forage crops. In Ladakh, a major feed source for dairy cattle is a plant called lucerne, which is commonly known as alfalfa.
Okay, alfalfa, got it.
And these plants are just remarkably good at pulling trace minerals out of the soil.
And cows eat massive quantities of this lucerne every single day. So the metals move from the soil into the water, into the plant, and then into the cow's digestive tract. And actually, this brings up a distinction we should probably clarify because people often conflate bioaccumulation with biomagnification.
They do, yeah. They're related, but they operate very differently.
Right, so think of bioaccumulation like saving pennies in a jar. Over time, as a single cow eats contaminated forage day after day, it stores up small amounts of metals. It takes them in slightly faster than its body can excrete them, so they slowly build up in its tissues.
That's a great way to put it. And biomagnification, on the other hand, is what happens across the entire ecosystem as you move up the food chain.
Exactly. Biomagnification is like a nesting doll. As you move up the food chain from water to plant to cow to human, the concentration of the metals gets denser and more dangerous. A single blade of lucerne might have a tiny, almost undetectable trace of lead. But a cow eats thousands of blades of lucerne, condensing all that trace lead into its body. Then a human drinks the milk from that cow over their lifetime, absorbing the concentrated output of all those thousands of plants.
That captures the compounding nature of the threat perfectly. The human at the top of the food chain takes on the cumulative burden of the entire ecosystem below them. Which leads us to a really pressing question. Mountains have always been made of rocks and minerals, so why is this risk suddenly a major concern in a place like Ladakh right now?
Because the landscape is undergoing this massive high-speed transformation. Reading the study's contextual data was honestly jarring. In 1996, Ladakh saw around 16,000 tourists. Fast forward to 2018, and that number exploded to over 323,000 visitors.
It's staggering.
It is. That is an exponential influx of people for a fragile, high-altitude desert to sustain.
And the infrastructure required to support that kind of population boom completely changes the physical chemistry of the region. I mean, between 2003 and 2017 alone, over 9,400 new buildings were constructed.
Wow, 9,000.
Yeah. That means a massive increase in construction materials, heavy vehicle traffic, diesel emissions, waste generation, untreated wastewater discharge. All of these are prime vectors for introducing synthetic heavy metals into the soil and water.
And we have to layer climate change on top of that human expansion, right? Rising global temperatures mean the glaciers in the Trans-Himalayan region are melting at an accelerated rate.
Exactly. If we connect this to the bigger picture, global warming is accelerating rock weathering, and when combined with explosive tourism and waste generation, these heavy metals are leaching into the soil and water much faster than before.
It's just a compounding effect. You have the accelerated release of geological metals combining with this sudden influx of human-generated pollutants.
Yeah, and the researchers recognize this shifting baseline. They realized that without rigorous data, any health risk would remain completely invisible. They needed to establish exactly what was in the local milk supply, so they set out to evaluate the concentrations of 10 specific heavy metals. They looked at aluminum, arsenic, boron, cadmium, cobalt, copper, iron, lead, selenium, and zinc, and they compared the data across both the summer and winter seasons.
I noticed in their methodology that they were incredibly selective about the milk they actually tested. They gathered 120 samples across 7 different villages, 60 in the summer, 60 in the winter.
Right, very balanced.
But they didn't just test any local cow. If you're just testing milk, why did the researchers have to be so incredibly picky about which cows they tested? They explicitly selected healthy, Jersey crossbred cattle of a specific age range, like 6 to 7 years old, with identical feeding practices. And crucially, they completely excluded any cows that were pregnant or in a dry stage.
Well, it goes to the heart of how environmental science isolates variables. You're right that the milk a local family drinks likely includes milk from pregnant cows. However, a pregnant cow's metabolism undergoes massive temporary shifts. She is aggressively mobilizing stored calcium from her bones to build the calf's skeleton. And because metals like lead mimic calcium, like we talked about, pregnancy triggers a sudden massive release of long-stored heavy metals into her bloodstream and milk.
Oh, wow. I see. So if you include a pregnant cow, her milk might show this enormous spike in heavy metals.
Yeah,
But that spike wouldn't tell you about the contamination in the current environment. It would be a reflection of her internal biological stress.
exactly. The researchers were trying to use the milk as a real-time bioindicator of the ecosystem, the soil, the water, the feed. By controlling for breed, age, diet, and excluding that metabolic chaos of pregnancy, they ensured they were measuring the steady baseline environmental exposure.
That makes a lot of sense. You have to prove the environment is the source before you can calculate the broader public health risk.
Yeah.
So they have these highly controlled milk samples. Now, we get to the part I kind of geek out over the laboratory methodology. Because you can't just put milk under a microscope to spot trace metals, right? They had to use acid digestion.
Yes, milk is a highly complex organic matrix of fats, proteins, sugars, and water. To isolate elemental heavy metals, they treated the milk samples with intense corrosive chemicals, specifically nitric acid and perchloric acid, and heated them. This violently breaks down and burns away all the organic cellular bonds.
Leaving just a clear liquid containing the elemental metals. And from there, they analyzed that liquid using a machine with a very sci-fi sounding name, the ICPOES, or inductively coupled plasma optical emission spectrometry.
It's an incredible piece of analytical technology. It's really the gold standard for this kind of environmental testing because it uses a plasma torch to heat the sample to thousands of degrees.
Wow.
Yeah, and at those extreme temperatures, the atoms of the heavy metals emit specific, unique wavelengths of light. The ICP-OES reads those light signatures. It's astonishingly sensitive, highly precise, and it can quantify multiple trace elements simultaneously from a single sample.
That is just wild to me. So after the plasma spectrometry, the researchers finally have their raw data. They have precise concentrations of 10 different heavy metals in the milk. But, and this is the tricky part, raw concentration doesn't directly translate to human danger. How do they take a spreadsheet of lab results and turn it into a tangible human health risk assessment?
This is where the methodology bridges chemistry and public health. They ran the raw data through internationally accepted risk assessment models. The entire process hinges on a foundational metric called the estimated daily intake, or EDI. This calculates how much of each metal a person actually consumes daily.
And that requires synthesizing a few different variables, right? You can't just look at the milk, you have to look at the human drinking it.
Correct. The EDI requires three specific variables. First, the concentration of the metal in the milk. Second, the recommended daily milk intake for Indian adults, which is roughly 300 grams per day. And third, they factor in the average body weight of an adult in Ladakh, calculated at 64.05 kilograms.
Right, because a heavier person can biologically process a slightly higher raw dosage than a smaller person.
Exactly. So once they have that personalized dosage, the ETI, they need to figure out if that dosage is actually harmful. That brings us to the target hazard quotient, or HQ.
Okay, what does that do?
The HQ estimates the probability of non-carcinogenic health effects from continuous exposure to individual heavy metals. We're talking about risks like kidney damage or neurological impairment. A value below 1 is an acceptable risk. The body can handle it. Above 1 means trouble.
Okay, and then people don't consume just one metal at a time. The milk contains a whole cocktail of these trace elements, so they use the hazard index, or HI.
Yes. HI is simply the cumulative risk, the hazard quotients of all 10 metals combined.
Here's where it gets really interesting for me. I like to think of it this way.
Yeah.
If EDI is the size of the meal on your plate, HQ is a speed limit for just one car on the highway, telling you if you're going too fast. And HI is checking if the entire highway of cars combined is going to cause a traffic jam in your body.
That is a highly accurate way to visualize it. You have to monitor the individual stress vectors, but public health ultimately depends on understanding that cumulative load.
Okay, so the researchers have isolated the variables, obliterated the milk with acid, mapped the light signatures, and run all these complex models for dosage and risk. After all that rigorous science, what were the actual results for the people of Ladakh? Is the milk safe to drink?
Let's start with the good news. For both summer and winter, the EDI, the HQ, and the HI were all well below the threshold of 1.
Oh, thank goodness.
Yeah, it's a huge relief. Currently, there is no significant non-carcinogenic health risk for the adult inhabitants from drinking local cow's milk.
That's amazing. But I did notice a surprising detail in the seasonal data. The levels of zinc spiked significantly during the summer months compared to the winter. What caused that?
What's fascinating here is that the spike wasn't caused by a sudden wave of tourists or industrial pollution. In the summer, when metabolic demands on dairy cows are higher, local farmers actively use zinc supplements in the cattle feed to encourage higher milk production.
Ah, so the milk acts as a real-time ledger of exactly what the farmers are doing. It reflects intentional human inputs just as clearly as it reflects environmental contamination.
Exactly. But while the non-carcinogenic results provide a sigh of relief, we do have to pivot to the darker side of the findings. They also ran models for carcinogenic risk, or CR.
Right, the risk of developing cancer over a lifetime of exposure.
Yes. They specifically evaluated the CR for arsenic, cadmium, and lead. And while the individual values were technically still below the maximum acceptable threshold, arsenic in both seasons, and cadmium specifically in the summer, are creeping dangerously close to the limit.
Meaning they aren't causing cancer today, but the concentrations are rising toward a tipping point.
Precisely. And when they calculated the cumulative target cancer risk, or TCR, adding the carcinogenic potential together, the combined load is hovering right near the threshold. Because of the heavy metals naturally found in local forage crops like lucerne, combined with the booming tourism and climate change, this is essentially a ticking clock that requires long-term monitoring.
So, what does this all mean for you listening? It means we can trace the impact of human expansion and a changing climate all the way down to a single drop of milk in one of the most remote places on Earth. Milk remains a vital life-sustaining food in the harsh Ladakh climate, and for now, thankfully, it is safe to drink.
It is, yeah. But this study acts as a crucial early warning system for them.
Absolutely. Which leaves you with something really vital to ponder as we wrap up today's deep dive. If the rapid modernization of a remote, high-altitude desert is already showing up in the molecular makeup of their local dairy, what invisible, slow-moving changes are currently being absorbed by the food chain in your own backyard? We often think of pollution as smog or oil spills, but perhaps the most profound changes to our environment are the ones we unknowingly drink every single day.